Hi there, Manuel for Entagma. This week again with the ripple solver. I already announced last time that I will bring part 2 of this video because we left out all the little things that make a working scene into a production setup. I want to do all these missing things today and show you how to do them. And the first thing that comes to my mind is that we used sort of a hack last time when using the deformed rest functionality of the ripple solver to update the geometry. That is not intended behavior. So today let's do it the proper way by using a SOP solver to update the simulated geometry directly. That's the first thing I want to do. So let's directly dive in and get started. Here we have the scene from last time, and if you remember, we have this point warp here that is doing all the deformation work. It's using the scattered points to deform the plane and then feed this deformed plane into the DOP-net, and the ripple solver cares about the rest. So inside we have this ripple solver here and the ripple object, and if you remember, the ripple object is set up by using two SOP paths. The initial SOP path that is telling the ripple solver which geometry to use, and then the rest SOP path which gives it basically a rest state to go back to. And it's simulating the difference between the two. Last time we used deforming rest. Today we don't want to use deforming rest anymore. What we want to do instead is update the simulated geometry. As you probably know, inside of DOPs you have geometry too, and this ripple object is in charge of creating and maintaining this geometry. You can see the geometry in the geometry spreadsheet. When you click on the geometry spreadsheet when inside DOPs, this view looks a little bit different than in SOP land. What you have here on the left is all the data that is necessary for the dynamic simulation. And here you have the ripple object, and inside you find geometry. And that is where all the geometry that is simulated is stored. If you click this, you see a somehow familiar view of all the geometry we have. And this is basically the plane we feed in. So this is what we specify with the initial SOP path. Instead of using this deforming rest, we want to update these points every frame with the deformations from the scattered points, and then the SOP solver will return to a not simulated rest. So how to do this? Well, what we want to do is we want to bring the point warp that is deforming into the DOP simulation. And the problem is inside we only have a ripple solver, and the ripple solver does not know about warps. So what we have to do is to split up the solving process in 2 steps. What you can do inside of DOPs is you can create a SOP solver. And the SOP solver allows you to use all the SOP nodes from SOP land inside of the DOP simulation to create or to modify simulation geometry. So let's create one, a SOP solver. Here it is. But the problem is now we have 2 solvers, the ripple solver and the SOP solver. And we have to choose which one to use, but we want to use both sequentially. So one after the next. The node that enables us to do this is called the multi-solver. Multi-solver, here it is. What this allows us to do is to chain many individual solvers one after the next and make them solve the same geometry. So what we can do using this node is to execute the ripple solver first and the SOP solver afterwards. To make this work, we have to connect the first input and the second input. The first input, if you hover over this input and middle click on it, it tells us this expects the objects to be processed. And the second input expects DOP data. So what we want is we want to connect the simulated object in this first port of the multi-solver, and then the second port takes all the solvers that we want to be executed on this geometry. So let's disconnect the ripple solver and connect it in here, like so. This setup gives us exactly the same behavior as before. So if I quickly pin the view 1 level up, dive inside and then press play, you will see that we get the same simulation we had last time, because it's basically exactly the same setup. It's just that this multi-solver is creating the connection between the ripple data, or the geometry, and the solver. But now what we can do is to add this subsolver to the chain. If I connect this to the multi-solver, what I now have is a DOP simulation that is first executing the ripple solver and afterwards the subsolver for every frame. And that enables me to modify the geometry after the solve step inside of this subsolver. Now let's do something useful with this freshly gained flexibility. I want this point warp not to deform the initial geometry anymore, but to deform the already simulated geometry in every frame. That's why I want to move this point warp inside of the DOPNet. So let's just copy it, dive inside, and now dive inside the subsolver. What you get here is 4 input nodes. DOP geometry, impacts, feedbacks, and relationship geometry. Don't care about these 3. These are for more complicated setups. We won't need them today. The DOP geometry is what gives you the geometry that is currently simulated. So in every frame, in comes the geometry that is simulated. And in our case, because of the multi-solver, this is a geometry already processed by the ripple solver. And this is the geometry we want to deform. So we paste the point warp here. But remember, the point warp used 2 inputs. First, the geometry to deform, and second, the scattered points that told the point warp where to deform the geometry. So we have to find a way to bring in the scattered points into this network. And we can do this by using an object merge node. Because we are in a subcontext inside of this subsolver, all the subnodes will work. The object merge makes no difference. Before we connect something to the object merge node, let's clean up our network a little bit. Because now we won't need this point warp anymore, so we can directly connect the transform to the DOPNet, and this connection is not necessary anymore. So disconnect it here. We will need the scattered points, but only to bring them in. So this is the first point where geometry goes into the DOPNet, and this is the second point where geometry goes into the DOPNet. As we will be referring to these 2 points from different nodes, it's good practice to mark them with a null to make it easier for us to find them. So I create a null in the middle here, and my convention is to color it yellow and call it in geo, and then a second null here for the scattered points. I call them in scattered points. Like so. Now it's easier for me to find these 2 nodes, and because I named them with capitals, they are listed at the top of lists. Inside of the DOP network, inside of the subsolver, I can now go into the object merge and just specify the in scattered points here. So this point warp will now deform the DOP geometry with the scattered points. If I enable this, it's hard to see. If I hide other objects, you might see it, that the scattered points come in. Great. Display flag on the point warp, disable point display again, and let's show the rock geometry. And now I have this subsolver deform the grid in every frame. If we disable the ripple solver for now, you see that the subsolver is generating all these deformations in every frame. But because we are now inside of DOPs, the deformations stay persistent and add up. Now, what's left is to change the settings on the ripple solver. So let's have a look at the ripple object. We want to change the initial subpath and the rest subpath, because now everything works differently and we want to untick use deforming rest. The initial subpath is now in geo, and the rest subpath is in geo too, because this is just an undeformed grid. And it will get deformed inside of the subsolver. So this initial subpath is only red on the very first frame. It won't be changed by the deformation and everything is good. And the rest the same. So it's just both subpaths are pointing to the same object. And if we now play, what we should get is a very nice ripple solver simulation. Maybe a little bit too high of a deformation, so let's quickly fix that, go into the point warp, and now you have to remember what we did in here. The fit is where we used to specify the radius of deformation, and it's currently set to 0.072, so let's decrease it a good amount to something like 0.01. Another test. A lot better, because now the radius is smaller, the whole deformation effect is not that prominent anymore, and it gives us immediately a very nice looking raindrop simulation. Look at this. Because now the ripple solver has a chance to do the proper thing, to analyze the curvature of the object properly and everything, and that means that the simulation already, by just changing this to a subsolver setup, is very much more natural and just better looking. The next thing we can do to make this thing look a little bit more natural and more interesting is to mess with the wave speed. Remember, here on the ripple solver you have this wave speed setting, currently set to 0.3. But this is Houdini, and that means that most of the parameters defining the simulation can be set through per point attributes, and that means they can be varied over the surface. That is the next thing I want to introduce to make this look more interesting. We will do this here on the topmost level before we bring the geometry into the .NET. We just define a per point attribute on the incoming geometry that defines the wave speed, and that will allow us to vary the wave speed. To do so, I create another warp. So create a point warp, and I put it here in front of the in-geo. And let's call this wave speed. Let's move the scatter out of the way. And the warps I use to color black to more easily see them. Let's get rid of this stuff, tidy up a bit, and dive into this wave speed thing. I just want to use a noise to generate a wave speed attribute. So create an anti-alias noise and connect it to the P attribute to create a different noise value for every point. And then I create a fit node, because this noise node returns values that are negative and positive, and I want to bring them in a range that I can use. So by just testing around, I've found that if I remap the range from -0.3 to 0.3 to a range of 0 to 1, it gives quite nice results. And now that I have this range normalized, I can use a parameter to give me a nice interface to be able to remap this. And the result of this is, of course, a spline ramp, wave speed. The result of this I feed to a bind node and, a bind export, because it's data we want to set, and this parameter will be called wave speed. You can look this up in the documentation. Now, to be able to see something, let's create a visualize and connect it here and make this show us the wave speed. Ramped attribute, wave speed, and I want the min and max values. And you see now you have this nice wave speed noise between 0 here and 1 here in the middle. And with the ramp parameter, you can alter this behavior by just moving these points around. So let's create a wave speed that is not higher than, let's say, 0.6. Like so. And let's see what this gives us. So rewind the simulation, dive directly into the .NET because we want to set the wave speed here on the ripple solver to 1, because now we are defining it as a per point attribute, and this value here acts like a multiplier. So if we put 1, it has no effect. Great. If we now press play, it doesn't look too different. I think I have to do a flip book for you to show you the effect. So let's quickly do that and then return as soon as it's done. So now you can see that the ripples are a lot slower here in this area, because there the wave speed attribute was very low, and here in this area where the wave speed attribute was high, the waves are a lot faster. We might want to vary the noise a little bit more to make this effect more apparent. So let's do this. Let's go here to the visualize, and in the anti-alias noise, let's up the frequency a little bit, and then maybe make this a little harder, such that the areas of wave speed have a higher contrast, and try again with the simulation. I again do a flipbook and return once it's done. So now you see the effect very clearly, and you see the nice effect it gives on the shape of these waves propagating. But we have the problem that we have areas with wave speed of 0, and that means as soon as the drop hits one of these areas, it won't simulate, and this leads to these strange bumps here. So we want to make sure that we don't have areas with a wave speed of 0, but with a low wave speed value. So this is the third thing that we want to do. Just make this, let's say, 0.2 and try again. And I think now the effect looks really decent, because look how naturally the waves behave. They have different speeds throughout the plane, and this leads to these distorted ripples that look very natural to me. So now that the effect looks nice, what's left to do? Well, we want to render this, and to be able to render this with absorption, and that is a property that is very necessary and very important for rendering water, we will need a volume, basically, so a closed polygonal shape. But what we have is just a plane. So the next thing we have to do is to turn this plane into a cube, basically, into a volume, to be able for an absorption shader to do its work. How can we achieve this? That is something we will append here at the end of this network. My plan is to select the boundary edge, then extrude it down, and then cap it off to create a closed volume. So by using a group node, I first create a group of the boundary edge. So go into the group node and set its entity to edges, because we want to select edges. And then on this edge tab here, disable this number tab, because we don't want to select by pattern. Instead, go to the edges tab, enable the edges tab, and then just check on shared edges. And this gives you just the boundary of this grid, which is very good. I call the group boundary to be able to refer to it easily later on. Now let's extrude this boundary by using a poly extrude. Poly extrude, append it, make it visible, and we want to constrain it to the boundary group. And now we want to not extrude by normal, but instead we want to transform the extruded front. Set the transform space to global, and then it's not z, but -y, and you get a very nice extrusion that is just going downwards instead of using the normal. This is looking nice, but if we have a closer look, you see that this edge is not straight, and the next operation will be that we want to create a polycap for this, which will have a hard time when the edge is not straight. So how can we make it straight? Well, first we want to output a selection, and we can do this by ticking front group here. Then we get a group extrude front, and we can use this to serve as a selection for the next node. Now just append a transform, and we can make this work only on the extrude front. So that means if we now transform this, you can see it just affects the boundary here. And now we want to just scale it to 0 in Y. And to be able to do this, the first thing we have to do is to move the centroid of this transform node to the common plane. And we can do this by just clicking Move Centroid to Origin. But that not only sets the pivot, but translates the nodes at the same time. So get rid of this translation. 0, 0, and 0, which leaves you with the pivot here. And what you can do now is to scale it down in Y to 0. And that has the effect of straightening out the border, because all these values will get scaled to 0 and share the same value afterwards. So what's left now is to cap it off. Unfortunately, we have this polycap node, and if we just append it, it creates a nice cap down here. And we are left with a volumetric block that can be used for a water shader with absorption to give nice rendering results. So now we created the right simulation, we optimized it by using wavespeed, and we created a volumetric polygon object for rendering. Now this can go into the renderer and give a nice shot. Thanks a lot for following me through all of this. I hope you learned something. See you next time.